On the morning of May 27, 1941, the German battleship Bismarck was subjected to one of the most brutal point-blank bombardments in naval history. Two British battleships and two heavy cruisers poured hundreds of large-caliber shells into its upper works, destroying command positions and silencing its guns. But Bismarck had already lost the ability to escape. The previous evening, the mighty vessel had been crippled, not by battleship artillery, but by a torpedo dropped from an obsolete, fabric-covered biplane. The mechanism of that failure would expose the most dangerous compromise in its design. It is the ultimate paradox of warship design. How did a nation build a machine so heavily protected that it could not be sunk, yet so architecturally flawed that it could not be saved? To understand the fatal trade-off hidden inside the Bismarck's blueprints, we have to rewind to a time when Germany had no battleships at all. Look at a naval map of Northern Europe. For a German admiral looking outward, the geography is a suffocating trap. Germany possesses a relatively small coastline, characterized by shallow estuaries, divided by the Jutland Peninsula. To the west, its ports empty into the North Sea. But to reach the deep, open waters of the Atlantic, any German warship had to pass either through the narrow, heavily mined English Channel, or take the long, brutal northern route between Scotland and Iceland. Sitting squarely across both exits was the British Isles, acting as a massive, unsinkable breakwater. And guarding that breakwater was the largest maritime force on the planet. For the British Empire, command of the sea was not a matter of prestige, it was a matter of basic survival. The home islands required millions of tons of imported food, oil, and raw materials every month, brought in by endless lines of merchant convoys. If an enemy could sever those Atlantic shipping lanes, Britain would starve. But threatening that lifeline meant bypassing the Royal Navy. The British Home Fleet, anchored in the cold waters of Scapa Flow, formed the core of a Royal Navy whose overall numerical strength Germany could not hope to match. In a conventional symmetrical naval war, the British could absorb horrific losses and still overwhelm any challenger through sheer mathematical superiority. Germany, meanwhile, possessed virtually nothing. Following the First World War, the Treaty of Versailles reduced the old German battle fleet to a small force centered on 6 obsolete pre-dreadnought battleships. The rebuilt navy, initially known as the Reichsmarine, was legally restricted to building new warships of no more than 10,000 tons standard displacement. This treaty metric, which calculated the weight of a fully equipped ship strictly without its fuel or reserve boiler water, was intended to keep Germany permanently crippled at sea. In the rigid hierarchy of naval power, 10,000 tons bought you a heavy cruiser. It was entirely inadequate for a ship meant to stand in a battle line and exchange fire with a 30,000-ton British dreadnought. Combined with Germany's geography, the treaty restriction created a tactical dead end. Treaty-compliant raiders could be hunted down by heavier British ships, while a fleet confined to the North Sea could be blockaded in its own ports. Germany could not challenge the Royal Navy ship for ship. To threaten Britain's Atlantic lifeline, it needed an asymmetric weapon. The man who believed he had the answer to Germany's geographic prison was Admiral Erich Raeder. Appointed head of the Naval Command in 1928, Raeder was a veteran of the First World War and had served as Chief of Staff to the commander of the German scouting forces at the Battle of Jutland. That apocalyptic clash in 1916 had left a permanent imprint on his strategic thinking. Raeder had seen what happened when a fleet tried to fight a purely conventional war in the North Sea. It ended up blockaded, mathematically outgunned, and strategically paralyzed. But Raeder also remembered the terrifying vulnerability of the ships that fought at Jutland. He had watched lightly armored British battlecruisers detonate and sink in minutes under heavy fire, sacrificed on the altar of speed. The experience of Jutland reinforced a broader conviction inside the German Navy. Whatever Germany built next could not sacrifice close-range survivability. In the early 1930s, the German Navy attempted to solve its treaty restrictions by building a class of 10,000-ton armored ships, widely known as pocket battleships. Armed with 11-inch guns, these unique vessels were designed as commerce raiders. They were faster than most existing dreadnoughts and outgunned any cruiser fast enough to catch them. For a brief moment, they were the perfect asymmetric threat, but the strategic window was closing rapidly. Recognizing the danger of these German raiders, the French Navy responded by laying down the Dunkirk class, fast, heavily armed modern battleships, explicitly designed to hunt down and destroy the pocket battleships. The British Royal Navy was also drawing up plans for its own new generation of 30-knot capital ships. Suddenly, Raeder's 10,000-ton raiders were too slow to escape the new battleships and too weakly armored to survive a fight with them. Raeder realized that if Germany was going to sever Britain's Atlantic supply lines, a 10,000-ton compromise was no longer enough. The doctrine of the lone surface raider had to be scaled up to unprecedented proportions. He envisioned a massive capital ship that could range far from friendly ports for weeks at a time, combining the reach of a commerce raider with the fighting power of a battleship. It needed the firepower to instantly obliterate heavily armed cruiser escorts, clearing the way to slaughter the merchant ships they protected. Yet, when the inevitable British battle fleet arrived to trap it, the ship had to possess the speed to simply turn and outrun the enemy. It was a brilliant operational theory, but as a list of engineering requirements, it was a profound contradiction. To achieve a sustained speed of 30 knots, a warship normally required a long, lean hull and enormous internal volume dedicated to massive boilers and turbines. But Raeder was also demanding 8 15-inch guns, which required heavy, structurally complex turrets. And, because of the lessons of Jutland, he demanded extreme armor protection, capable of surviving point-blank gunnery in the poor visibility and brutal weather of the North Sea. Heavy armor requires a wide, deep hull to support thousands of tons of dead weight, the exact opposite of a lean, fast ship. Admiral Raeder was demanding a strategic miracle on a piece of paper. He had defined the doctrine, set the requirements, and provided the political willpower. But Raeder was not a naval architect. He could not draw the blueprints, calculate the metacentric height, or weld the steel. Raeder had his doctrine. Now, he needed someone to actually build the impossible ship. The task of turning Admiral Raeder's strategic demands into physical geometry fell to the Konstruktionsamt, or K-Amt, the German Naval Construction Office. At its center was Ministerial Rat Hermann Burkhardt, the chief naval architect who would serve as the principal draftsman for the new warship. When Burkhardt's design section received the requirements for a heavily armored, 30-knot raider armed with 15-inch guns, they immediately ran into a mathematical wall. The first wall was political. In 1935, the Anglo-German Naval Agreement was signed, theoretically normalizing naval relations between London and Berlin. Under the agreement, Germany accepted a total fleet tonnage fixed at 35% of the Royal Navy and undertook to observe the wider international limit of 35,000 tons standard displacement for an individual battleship. The second wall was geographical, and it was entirely unyielding. Germany's naval infrastructure dictated that any major warship had to operate out of the shallow estuaries of the Elbe and Jade rivers. More importantly, the ship had to be capable of transiting the Kiel Canal, the vital artificial waterway connecting the Baltic Sea to the North Sea. The locks of the Kiel Canal were fixed concrete boxes, imposing strict limits on the length and beam of any ship passing through them. draft was constrained by the depth of the canal, its approaches, and Germany's shallow estuaries. These political and geographical limits tightened Raeder's existing design contradiction. The engine's armor and hull length required for his fast, heavily protected Raeder now had to fit within treaty tonnage, canal dimensions, shallow approaches, and a workable draft. The solution was not simply to grow downward, but to spread the displacement through a broad hull. The K-Amt engineers pushed the ship's beam to roughly 118 feet, balancing canal clearance, stability, machinery space, armor, and the need to keep the draft within workable limits. But the math of this widened, elongated, heavily armored fortress revealed an uncomfortable truth. Even with every conceivable weight-saving measure, the blueprints demanded a ship that was fundamentally illegal. It could not be built for 35,000 tons. Rather than compromise the ship's survivability or speed, the German Naval Command and their political sponsors in Berlin made a simple, brazen choice. They would build the ship they needed and lie to the world about its size. While officially declaring the new battleship to the British as a treaty-compliant 35,000-ton vessel, Burkhardt's final design displaced about 41,700 long tons at standard displacement, roughly 42,300 metric tons, and about 49,100 long tons at full load, rising above 50,000 under some combat loading calculations. It was a massive, state-sponsored deception, turning the treaty limit into a phantom number to conceal one of the largest battleships completed by any European navy before the war. Burkhardt had secured the massive geometry required to support Raeder's vision, bypassing both the British diplomats and the concrete walls of the Kiel Canal. Burkhardt had his massive, wide hull. Now he had to decide how to protect it and how to move it. On the drafting tables of the K-Amt, the sheer size of the new hull offered Hermann Burkhardt a massive canvas. But allocating that 41,700 tons of steel required ruthless compromises. The most critical debates centered on two features that would ultimately dictate the ship's fate: how it would absorb damage and how it would move. In the 1930s, naval architects in the United States and Britain were shifting toward a concept called all-or-nothing armor. Anticipating modern naval battles fought at extreme ranges, where shells would plunge downward from the sky, they placed massive, heavily armored boxes over the ship's vital organs and left the rest of the hull entirely unprotected to save weight. But the conservative leadership of the K-Amt, haunted by the ghost of Jutland, rejected this modern trend. They believed that the brutal weather and poor visibility of the North Sea would force ships to fight at closer ranges, where shells flew on flat, horizontal trajectories. They mandated a protective scheme directly inherited from the dreadnoughts of the First World War, the Böschung, or turtleback armor. Instead of relying solely on an incredibly thick outer wall, Burkhardt's design utilized a heavy main belt backed by a sharply sloped internal steel deck that angled down to meet the bottom edge of the outer armor. If an enemy shell pierced the outer hull, it would strike this angled internal deck and deflect upward or shatter, leaving the ship's deep magazines and boiler rooms completely untouched. The advantage of the Iron Turtle was undeniable. At close range, the layered armor made direct penetration of the magazines and machinery spaces extraordinarily difficult, reducing the risk of a sudden magazine explosion or rapid loss of the ship. But this World War I blueprint carried a severe modern trade-off. To afford this layered, distributed lower protection, the upper decks had to remain relatively thin. The armored conning tower was formidable, but the communications cables, optical instruments, antennas, and exposed fire control directors above the citadel remained vulnerable to shellfire and blast. Burkhardt was designing a ship that could survive massive structural punishment, but ran the grave risk of having its brain and eyes rapidly shot away, leaving a blind, floating fortress. This massive armor scheme was stretched over an exceptionally long central citadel. To ensure mechanical reliability and a high rate of fire, the designers had chosen to mount the ship's 8 15-inch guns in 4 twin turrets, rather than grouping them into heavier triple or quadruple turrets like their French or British rivals. 4 separate turrets meant a longer, heavily armored box was required to protect the separated ammunition hoists. This sprawling armored citadel ate up enormous amounts of internal space and weight, forcing severe compromises in the ship's propulsion. To push the massive hull to Admiral Raeder's demanded 30 knots, the ship required an immense complex of high-pressure steam boilers and turbines. Most rival navies distributed this kind of power across 4 propeller shafts, providing maximum redundancy. Burkhardt's team, desperate to save weight and compress the machinery spaces into the remaining hull volume, opted for a 3-shaft layout. The advantage of this choice was significant. Dropping the 4th shaft saved hundreds of tons of machinery weight and allowed for excellent watertight compartmentalization in the stern. But the architectural cost was the creation of a fatal Achilles heel. The center propeller shaft ran straight down the midline of the ship, sitting directly ahead of the vessel's 2 parallel rudders. This massive central propeller disrupted the clean flow of water over the steering surfaces. Worse, a 3-shaft layout severely limited the ship's ability to steer using its engines. If the rudders were jammed, widely spaced shafts could sometimes provide limited control through differential thrust. Bismarck's 3-shaft arrangement and closely grouped stern geometry offered less leverage, but no propulsion layout could guarantee control against a damaged rudder dragging hard in the water. The compromise left the ship with weak emergency steering authority if the rudders were disabled. With the design compromises fixed on paper, Burkhardt's project moved to the shipyard. On July 1, 1936, Bismarck was laid down at the Blohm and Voss shipyard in Hamburg, turning Hermann Burkhardt's massive blueprints into steel. Translating a 41,700-ton secret into a physical warship was a monumental industrial undertaking. For nearly 3 years, a relentless river of steel flowed into Slipway 9 as thousands of dockyard workers assembled the predominantly welded, exceptionally wide hull. The sheer scale of the ship tested the limits of German heavy industry, requiring enormous coastal cranes and the dredging of harbor channels just to accommodate the vessel's immense displacement. On February 14, 1939, the empty, unarmored hull finally slid into the Elbe River, christened as the Bismarck. It was a moment of supreme political theater, attended by Adolf Hitler to project the illusion of a reborn German empire. But for the engineers of the K-Amt, the true test lay not in the launch ceremonies, but in the cold, isolated waters of the Baltic Sea. By late 1940, the Second World War was already raging, and the completed Bismarck was sent to the Baltic for its exhaustive sea trials. This was the moment of truth, the physical audit of Admiral Raeder's strategic demands and Burkhardt's architectural trade-offs. Initially, the trials were a resounding triumph. The massive high-pressure steam machinery worked flawlessly, generating over 150,000 horsepower and pushing the armored Leviathan to a top speed of just over 30 knots. Raeder had his fast raider. Furthermore, the immense 118-foot beam gave the ship great initial stability and a powerful tendency to return upright. But this did not make the hull motionless. The same high stability could produce a short, lively roll in rough water. Even so, the broad, rigid platform gave Bismarck's optical rangefinders and heavy turrets a formidable base for accurate fire. But then, the trial cruise tested the ship's Achilles heel. During the sea trials, the crew tested whether the ship could be controlled by altering propeller revolutions after a steering failure. The exact rudder positions used during these tests are not securely documented, but propeller thrust alone gave Bismarck poor directional control. The result confirmed that loss of the rudders could leave the ship effectively unsteerable. The engineers logged the failure, but the brutal timeline of the Second World War would not wait for a complete structural redesign of the stern. Admiral Raeder desperately needed his raider in the Atlantic before the United States could enter the war and tip the balance of naval power permanently. The Bismarck was cleared for combat. The fatal flaw was noted, but the raider was sent out to meet the enemy. In May 1941, Admiral Raeder's strategic gamble was finally unleashed. Operation Rheinübung sent the Bismarck breaking through the Arctic mists into the North Atlantic. But before the raider could vanish into the vital merchant shipping lanes, the Royal Navy intercepted the German battleship in the freezing waters of the Denmark Strait. This famous clash against the pride of the British fleet, the battlecruiser HMS Hood, and the new battleship HMS Prince of Wales, was not merely a tactical engagement. It was the first brutal live-fire test of Hermann Burkhardt's K-Amt blueprints. In the Denmark Strait, the broad hull provided a stable gunnery platform, while Bismarck's effective optical fire control system, experienced gunnery team, and 4 mechanically reliable twin turrets produced a relentless rhythm of fire. Within minutes, a German 15-inch shell apparently triggered the explosion of Hood's aft magazines, destroying the largest warship in the Royal Navy. The precise path of the fatal projectile remains unconfirmed, but the result violently demonstrated the effectiveness of Bismarck's gunnery. But the destruction of the Hood shocked the British Admiralty, triggering a massive, desperate response. Every available British warship in the North Atlantic was ordered to hunt down the German raider. Bismarck still had the speed to escape, but a serious hit forward had flooded compartments, contaminated or cut off fuel, and forced Lutyens to seek repairs in occupied France, even as the ship maintained high speed. Burkhardt's blueprint was outrunning the enemy battleships exactly as Raeder had envisioned. Then, the fatal compromise hidden in the stern of the ship was exposed. In the fading light of May 26th, a squadron of obsolete, fabric-covered Fairey Swordfish biplanes, launched from the British aircraft carrier HMS Ark Royal, descended upon the fleeing battleship. They carried slow-moving aerial torpedoes that barely packed enough explosive power to dent the Bismarck's massive main armor belt. But one of those torpedoes struck the stern, detonating directly against the unarmored steering compartments. The explosion was catastrophic not for the hull, but for the ship's nervous system. The blast wrecked the steering system and left at least one rudder jammed at a damaging angle. Surviving accounts disagree over the exact final positions of the 2 rudders. Deep inside the crippled ship, damage control teams in breathing and diving gear entered the flooded steering spaces, struggling to inspect the damage and restore or disconnect the jammed mechanism. On the bridge, the captain attempted the exact maneuver that had failed during the Baltic Sea trials. The engineering crew desperately manipulated the 3 propeller shafts, trying to steer the vessel through asymmetrical thrust by running the starboard engines at full ahead and the port engines in reverse. It was useless. The failure documented during the Baltic trials had become operational reality. With the rudders disabled, differential thrust could not restore control. The most formidable surface raider on Earth was now fundamentally unsteerable. Drifting helplessly off course, turning in endless, agonizing circles in the open ocean, the Bismarck could only wait for the entire British home fleet to arrive. On the morning of May 27, 1941, the British home fleet finally closed in. 2 heavily armed battleships, HMS King George V and HMS Rodney, supported by heavy cruisers, opened fire on Bismarck at close range. As thousands of British shells of all calibers, among them hundreds of 14 and 16-inch projectiles, rained down upon the German warship, the conservative World War I-style armor performed a terrifyingly effective job. The heavy main belt and the sloped internal turtleback deck made direct penetration into the magazines and central machinery difficult, but they could not prevent cumulative flooding, shock damage, or every hit from reaching vital spaces. The ship absorbed an apocalyptic level of structural punishment that would have instantly detonated any lesser vessel. The ghost of Jutland had dictated the creation of a ship that could survive close-range, heavy-caliber gunnery without catastrophically exploding, and Hermann Burkhardt's blueprint delivered exactly that. But the fatal trade-off embedded in that distributed armor scheme was immediately realized. Because much of the ship's protection was concentrated around the belt, armor slopes, and armored decks, equipment above the citadel remained far more vulnerable. Within the first 30 minutes, repeated hits and blasts wrecked exposed command positions, communications runs, and fire control equipment, while even the heavily armored conning tower became isolated and ineffective. The ship's towering, highly sensitive optical rangefinders and central fire control directors were shattered. Baron von Mullenheim-Reckberg, the highest-ranking officer to survive the battle, later described a rapid collapse of communications as command posts and circuits were destroyed one after another. With centralized fire control gone, the surviving turrets shifted to sporadic, ineffective local fire before being silenced. The ship had suffered a complete mission kill. Its command and combat functions were destroyed even as the hull remained afloat. German survivors reported that scuttling charges and deliberate flooding measures were initiated in the final minutes, while British shellfire and torpedoes had already caused catastrophic damage and progressive flooding. The burning ruins slipped beneath the Atlantic under the combined effects of battle damage, torpedo hits, flooding, and probable scuttling. The exact balance remains disputed. The physical ship was gone, and the loss dealt a severe blow to Raeder's surface raiding strategy. Bismarck had shown how vulnerable an unsupported capital ship could become when pursued far from home by carrier aircraft and concentrated naval forces. Later Admiralty reports documented the steering damage, gun battle, torpedo attacks, and survivor testimony, but did not issue a sweeping design verdict. The broader implication emerged from the campaign itself. Heavy protection could preserve the hull without preserving the ship's ability to maneuver or fight. Today, Hermann Burkhardt's masterpiece rests roughly 4,790 meters, about 15,700 feet, deep on the floor of the Atlantic Ocean. The wreck still reflects the paradox built into the ship, though not as perfectly as legend suggests. The armored central hull lies upright and remains largely recognizable, but the stern is separated and the wreck bears battle damage, structural collapse, and the violence of its descent to the seabed. Much of the upper works and exposed fire control structure has been torn away or crushed. It remains a permanent, steel monument to a brilliant and flawed machine.